if you have any question about the tutorial. Okay, if not, we will move to chapter 2. Okay, in chapter 1, we talked about classification of vibration. If we can just go back a little bit. Okay, that classification of vibration was one of them was the free vibration, and I gave examples about pendulum. If initial angle is given, then the pendulum will oscillate with the natural frequency. We call it natural frequency, and it is function of L and M. Also, as you can see, for different values of M, the natural frequency will be different. And then we have spring mass system. Again, will have a natural frequency that is function of K and N. Okay, and then the number of natural frequencies equal to the number of degrees of freedom. Okay, so this is all systems possessing mass and elasticity are capable of a free vibration or vibration that takes place in the absence of external excitation. So not any object will oscillate or will vibrate, not any system will vibrate unless it is a system that consists of mass and elasticity. It will vibrate in free vibration. Okay, and the definition of a free vibration is the vibration that takes place under the absence of external excitation. I mean, there is no force imposed on the system to let it oscillate. So it is oscillating under its own after initial disturbance from the equilibrium. The free vibration is a natural phenomena, a physical phenomena that occurs whenever the system is disturbed from equilibrium. So what we will do here is to find the natural frequency. Okay, so the purpose from the free vibration is to find the natural frequency. We can do this mathematically, okay, by deriving the equation of motion and then find the natural frequency. Also in practice, if there is a suspension that is expected that the vibration is occurring at natural frequency, then they measure the vibration under free vibration, and then they measure the natural frequency. It's done by using some sensors and frequency analyzers. Okay, that some instruments that can measure the vibration and then make the processing to find the frequency. So the natural frequency will be determined in free vibration. And I told you about force vibration last time in chapter 1, that the vibration that takes place under external excitation, which means there is a force with a excitation frequency. Okay, so the excitation frequency is not necessarily equal to the natural frequency. So one way of determining the natural frequency is by letting the system to oscillate under free vibration. So either by you can determine the frequency by using some instruments, accelerometer maybe, and some other devices that record and process the measured vibration to find the natural frequency. Or we can do this by by mathematically. We will do it here in this chapter. Okay, so we will you write the equation of motion, which is an ordinary differential equation, and then I will tell you how that nature frequency can be obtained from the nature frequency. For a spring mass system, the nature frequency will be a function of K and M, and we call the system translational system. So any system that has a translational type of motion, we will model it as a spring mass system with massless spring. So this is part of what we will do in this chapter, that if a system is oscillating, but it is in translational motion, then we will model it as mass and massless spring. And you can have also a damper as well. And I told that a viscous damper can be part of the system. It is not necessarily to be part, but if it is a part of the system, it will damp the vibration. It will act as an energy absorption that will not let the system to oscillate without decrease in amplitude. So it will force the system to stop. We will talk about this in this chapter as well, with that we will consider system with damped and undamped, undamped and damped system. Okay, if the system is rotational, then it could be a simple pendulum, it could be a compound pendulum, okay, or it can be in rotational vibration like shaft. Okay, so we have 3 types of models: spring, massless spring carrying a mass, simple pendulum, and shaft and a disc. So we will have actual systems that will model them, or called the practical vibration system. We will model them in most cases as a spring mass system, or and a viscous damper, or it might be also as a simple pendulum or torsional vibration. So for a spring mass system, the elements will be the mass, and the mass and the force and the mass is governed by the Newton second law, that sum of forces equal to mx double dot. So x double dot is the acceleration, and we need to write it in this form rather than a, and we don't write f equal to ma. So we substitute the definition of a, which is the double dot, that is d square x by dt square. This is the acceleration, and the reason is that a is unknown, the acceleration is unknown. In dynamics, we did that a is either 0, we call it uniform motion, or a equal to constant. We focused on those 2 cases. Okay, in vibration, that acceleration is not constant; it is changing with time. So it's better to keep the definition of the acceleration as it is. That is d square x by dt square, and for short, we just write it as x double dot. The spring, the force in the spring is governed by Hooke's law, which is F equal to kx. X here is the change in length, or which is displacement. In the vibration system, that x is measured from equilibrium. Okay, so we call x is the displacement. Okay, and k is the spring constant, or called stiffness, spring stiffness in Newton per meter. And the viscous damper, the relationship of the force is related to velocity. the force is given as F equal to C x dot, where x dot is the velocity. This is also a linear relationship, where C is called damping coefficient and given as Newton per meter per second, which is the unit of force divided by the unit of velocity. And then you can make it simpler, that is a Newton second per meter. So the forces, those are the three forces for spring mass system, that the force is directly proportional for the mass. The force is directly proportional with acceleration. And the force on the spring is the force that is directly proportional with displacement. And then in the damper, viscous damper, that the force is directly proportional with the velocity. All those relationships are linear. So we'll start with NDAM. So I told you that we will also talk about undammed system. So the first part is going to be about undammed system. So or system under free vibration, undammed free vibration. The model will be spring mass system, as you can see here, that the spring, if it is massless and it is unloaded, it will have unstretched length. Okay, so this is the spring when it is supported from one point and hang. Then this is the no load here, massless spring. Then there is no load on the spring. The spring will have the unstretched length. We call it L0. So this is unstretched length. Or undeformed. When you add the mass on it slowly, it will go down and become in equilibrium. So here a mass is added, and this is called equilibrium position. The distance moved from here to here, since this is equilibrium. This distance is, we name it delta, and delta is called statical deflection. That means the amount of stretch in the spring at equilibrium. Okay, statical deflection. The vibration will start about this line. Okay, vibration will be about this line, about the equilibrium line. So as you can see from this figure, when you don't add the spring, when you don't add the mass, the spring is under, the spring is unstretched, and that position is called unstretched position. When you add the mass slowly to the spring, it means you are not exciting the system. You are not allowing the system to oscillate under free vibration. So just holding the mass until it reaches the equilibrium position. Then the spring will be, of course, longer because it is under tension, and it will have a change in length. Okay, which is going to be delta. So the new length is L0, is L, and delta equal to L minus L0, the change in length. But we give it a name as statical deflection because this is the deflection during equilibrium only. So this is the static part. This is not moving here. And then when you give initial condition, it will oscillate. Okay, so this is the equilibrium. This is the equilibrium position here. After adding the mass, and then you can put the forces on the mass. We have the weight and the weight of the mass, and we have the spring force, which is by Hooke's law, is K times the change in length, which is delta here. And this will be for equilibrium, we have sum of forces equal to 0, and this will be K delta. I'm going to use, K delta minus the weight equal to 0. And since this equation is equal to 0, you can also write W minus K delta, right? There is no problem here. It's the same because equal to 0. And then you can find delta if you want. Delta is W over K, and you can substitute for W is mg over K. Now in in vibration, also we need to draw the free body diagram. Okay, this is the free body diagram for equilibrium. Also, this is another free body diagram for vibration. This is for equilibrium, and this is for the vibration. Now, the vibration is not one point, or it is not one position, but the free body diagram we do is assuming, or we do it in the direction of positive x direction. Okay, so we have to assume a positive direction for x. As you can see here, downward, x is given, is shown as downward motion from equilibrium. So the vibration will be about this line. You can put the free body diagram above the static equilibrium position, or you can make it below. It doesn't matter. So you have to, whenever you draw the free body diagram, you have to define a positive direction. So x here is positive downward. Okay, which is below the static equilibrium. This is the definition. This is the assumption. Okay, let x, or assume x is positive in the downward position, below the static equilibrium. Then the spring force will be more. The spring force will be K delta plus Kx, or K times delta plus X, which is the delta plus X is the total change in length in the spring. And the weight is still the weight. It is the same. Now here, although the free body diagram is drawn at in the positive direction, but this is not at equilibrium. This is at when the mass is moving with acceleration. And this is only an instant of time, or it's called arbitrary position. This is not at a given or specified value of x. X is function of time. Okay, so x is not constant. X is function of time. So this is an arbitrary position, or like snapshot. X is function of time. then we know that at this position, okay, I can say here, this free body diagram is free vibration. It is a free body diagram or vibration at arbitrary position. Not at any specific position. At arbitrary position in the positive direction. Okay, this is not at the extreme, this is not at the zero, this is anywhere. Okay, so we assume that it is between the zero and maximum position. And so it had an acceleration x double dot and a velocity as well. Okay, here since the system is undamped, the velocity will not be shown. So what you can do at vibration is that you take sum of forces equal to m x double dot. For the sum of forces on the left hand side, we have to define the positive direction of forces. So downward is positive. If you want to take downward positive, which is in the direction of x, positive x, which is the direction of x double dot. That is positive. So the forces downward are positive, and the forces downward is only the weight minus k, and the spring force is k delta plus x equal to mx double dot. Okay, if you draw the free body diagram above, okay, then that will be k delta minus x. But with the definition of that x is downward positive, when the mass is above the static equilibrium, x is negative. So delta plus x, it means it is delta with minus x, because x will have will include the sign. X include the sign. So if x is positive, then it's when the positive direction, it means its sign is positive. When the mass is above the static equilibrium, it is in the negative direction, and the value of x will be negative. So it will be changing. Okay, we have two equations here. This equation is the static equilibrium equation. That is W minus K delta equal to 0. And when you expand this equation, this will be W minus K delta minus Kx equal to Mx double dot. So you can see that this equation is appearing again, which is the static equilibrium. Now, W minus K delta equal to 0, there is no time here. So this is always 0. So you can remove these two terms and get, as a result, minus K delta minus Kx equal to Mx double dot. And the equation, the final equation, is independent of the weight, and it is independent of delta, except that K is related to delta here. Okay, this was K here. Okay, so it is there is a relationship between K and delta, or delta is dependent on K this way from the equilibrium, that the amount of static deflection depends on how stiff is the spring. Okay, so we reach to the final equation, that is minus Kx equal to Mx double dot. And the equation is familiar, by the way, to what we did in chapter 1. Okay, so when you apply Newton's second law in the vibration free body diagram, you get mx double dot equal to sum of forces, and we take downward positive, which is the definition, the positive direction, the definition of the positive direction of x. So it is W minus K delta plus X. And since K delta equal to W, which is the equilibrium equation, then you will end up with mx double dot equal to minus kx. Okay, this equation is familiar, I said, to what we did in chapter 1 about harmonic motion. So if you just divide by x by n both sides, you get minus k over m x. Okay, this is the condition for harmonic motion. Now k and m are not changing with time. Those are constants. The spring stiffness is a constant, is a spring constant, and m is also a constant. So this equation is called harmonic condition. Okay, so I can take you back to chapter 1 and harmonic chapter 1 lecture 3 harmonic motion, and we call this is the condition for harmonic motion. Here it was given as omega, and in that the constant is omega squared. And in chapter 2, the equation we find is also constant. This k over m is constant, so you can call this value omega squared. So it means that omega squared is equal to k over m. Just when we compare with harmonic motion. Okay, so this is the harmonic motion. Okay, this is the harmonic condition, which means that x is harmonic. The harmonic motion, it means that x will be given as sine or cosine or addition of sine and cosine of the same frequency. This frequency, omega, is frequency, and we specifically differentiate this omega or designate this omega as omega n. Omega n. We name it omega n, which means the natural n is for natural frequency. Okay, so it is omega n squared, just to make a specific denotation of the or designation of the type of the frequency. That is this is the natural frequency. The equation can be rearranged as a differential equation as well. This harmonic condition is in fact is a differential equation. If we take you put the terms all in one side, okay, then this becomes, you replace k over m with omega n squared, and this becomes x double dot plus omega n squared x equal to 0. Now this equation is what is a differential equation. Okay, this is a differential equation with two terms. There are two terms. X double dot plus omega n squared x equal to 0. Equal to 0, it means this is homogeneous. Homogeneous differential equation. There is no forcing, which makes it no external force. So although there is no external force applied on the system, but the system has a differential equation, which is the equation of motion, which means there is motion. Okay, x double dot plus omega n squared. The terms, if we go back to before dividing by m, it is m x double dot plus kx equal to 0. This n and k are constants. Also, omega n squared is a constant. Okay, so as you can see, it is not function of time. Omega n is omega n squared is k over m. So omega n is also constant. This equation has constant coefficients. M and K are constant. And it is second order because we have second derivative. The highest derivative in the differential equation is 2. So this is called second order. Ordinary because it is the derivative with respect to time. There is one independent variable. Ordinary, second order ordinary linear differential equation. Why it is called linear? Because the terms in X are given as linear. That is X double dot is a linear term and X is also a linear term. Okay, if it is X squared, then this is called nonlinear or X cube. Some of the problem there is X cube is nonlinear term. So here we have to power 1, that is X double dot to power 1 and X to power 1, then we have linear terms and makes the equation to be linear differential equation. And this was one of the classification of vibration as well, that there could be linear vibration or could be nonlinear vibration. The solution to the differential equation is the second approach that we need to do. But the first thing, after evaluating the differential equation, you have reached to the goal. The first goal we set for ourselves is to find the nature frequency. So once you reach to the differential equation in this form, you know that after dividing by m, okay, divide by m, then you reach to the final differential equation. The coefficient of x is the nature frequency squared. So without solving the differential equation, we reach to the first goal we set that for ourselves. We need to find the nature frequency. So this can be obtained by observing the final differential equation, which is the coefficient of x. You make x the coefficient of x double dot unity. It means dividing by n, or you divide by the number by the constant in front of x double dot to make the coefficient of x double dot unity. Then the coefficient of x is the nature frequency squared. So for example, we have 2x double dot plus 25. Okay, let's say 50x equal to 0. What is the nature frequency here? Divide by 2 and then reach to x double dot plus 25x equal to 0. Then omega n squared is 25. And then you take the square root, you get omega n equal to 5 radian per second. And of course, there is no negative frequency. We take only the positive value when you take the square root. Now, we are saying that omega n square is the nature frequency. So we have to check the units. Okay, check the unit. We should get the unit of radian per second. So I'm saying here it is radian per second. I need to show you that it is radian per second. So the unit of omega n square is the unit of k over n. Okay, so omega n square equal to k over n, and the units will be the unit of k is in Newton per meter, and the unit of m is kilogram. Okay, and Newton is a derived unit, and Newton is kilogram meter per second squared. Okay, multiply by meter divided by kilogram. And you can see that kilogram and kilogram cancel out, and meter cancel out, and this will be 1 over second squared. And when you take the square root, omega n, unit of omega n is radian per second. You might wonder that there is no radian shown here in the 1 over s squared, because radian is not one of the units. It's not a unit. They can add it this way, radian per second. When you take the square root, the units of omega n is radian per second, which is called circular frequency. Omega n is the circular natural frequency, but usually we drop the word circular for short, we just call it natural frequency. So one of the objectives is to find natural frequency. It can be found from this equation by observing the coefficient of x. After you make the coefficient of x double dot equal to 1. Okay. Then the second thing we need to find is the position, which is x. X is function of time. In dynamics, usually we find points or position at given instant of time, not for all time. For example, I just want you to follow what I'm saying. This is why I take you back to dynamics. If you have a spring with massless plate, and then you have a mass, okay, and there above the spring with certain height h. Okay, we usually relate 2 points. We take this point as point number 1, and the second point is when the spring is under maximum deflection. This is point 2. And then we can find this distance. We call it x, for example, capital X. So what you did in dynamics is relating point 1 and point 2 only. And the reason is to find the maximum deflection of the spring when the mass drop on the spring. So we let the velocity equal to 0 and we apply conservation of energy and so on, right? But we are not finding x with time. Okay, we are not finding x with time unless you make x known. What is the velocity when x is, let's say, 0.1 meter or whatever. Here we'll find x for all time, including this problem. Okay, including this problem can be solved using what I'm doing now in with the spring mass system. Okay, if the mass becomes engaged with the plate, the massless plate, then this will be a vibration problem. So as you can see, the main difference that we are doing here in this course as compared with dynamics is to find the frequency, and which is not even mentioned in the course, dynamics course, and also the displacement with time, not at point, not the maximum. Okay, and that can be achieved by solving the differential equation. Okay, so the differential equation, ordinary, the above, which is mean this one, is the ordinary differential equation with constant coefficient. The solution is given by x. There is only one solution. I mean, there are 2 terms in the solution, but usually differential equation, you will assume that x equal to exponential e to power st. Okay, so the solution is, in general, you will assume that x equal to e to power s st, where s is constant. We will do this next section. And then you will find that s equal to, after substitution, this will be, you assume You assume this solution, and then you substitute in the differential equation. You will get the second derivative of x. It means this will be s squared e to power st plus omega n square e to power st equal to 0. So you can divide by e to power st. And this will give us that s squared equal to minus omega n squared. So you take the square root, you get s equal to plus minus I omega n. I equal to square root of minus 1, which is the complex. E to power, now I will substitute x equal to e to power st, and s now is plus minus I omega n. This can be reduced to, you can put a constant here equal to e to power plus minus. If you put c here, this will cancel out. Okay, so this will be c, and this will be c as well here. So c will cancel out. So this will be equal to c using, this is called Euler equation. So this will reduce to cosine omega n, this is t here, omega n t plus I sine omega n t. So usually we just call this a sine omega n t plus b or c, just a constant, b cosine omega n t. Okay, you can use c or you can use, okay, I will use c, no problem. Okay, c is a constant, a is a constant. Okay, so just to make it consistent, I will use here b. Okay, so this is b, so that you don't confuse. Okay, b times I is another constant, just call it a. So a sine omega n t plus b cosine omega n t is the solution. Okay, so the solution is x equal to a sine omega n t plus b cosine omega n t. This is the solution of the differential equation, which give us the displacement of the mass for any value of time. Okay, for any value of time. What is a and b? A and b are the two necessary constants of integration of the differential equation, and this can be evaluated from the initial conditions. If there are no initial conditions, there will be, it means that A is 0 and B is 0. There is no vibration. So the vibration will take place if there is initial disturbance. Those initial conditions, we call them disturbance. Okay, initial conditions or disturbance, initial disturbance. A disturbance from equilibrium. Okay, so the disturbance or initial conditions are two. The initial displacement and initial velocity. Okay, it can you can have both of them given non-zero, or one of them is non-zero. If both of them are 0, it means X is 0 for all time. For example, the pendulum, when the pendulum is not disturbed from equilibrium, it will stay vertical. So unless you give initial disturbance, it will not move if you don't give initial disturbance. Now the solution or those constant can be found from by applying the those conditions. So X at 0 equal to A sine 0, which is sine 0 is 0, plus B cosine 0 is 1. So this means B is equal to the initial displacement. And initial velocity is, if it is given, then this will be A omega n cosine 0 when you take the differentiation minus B omega n sine 0, and cosine 0 is 1, so this will be A omega n, and sine 0 is 0. So this gives us A equal to X dot at 0 divided by omega n. So when you substitute for A and B, you get the final equation of the solution. Okay, that is X equal to A, and A is X dot at 0 divided by omega n sine omega n t plus X at 0 cosine omega n t. This is the solution of the differential equation. So we don't do the solution again. I mean, I will not ask you to solve the differential equation again, using the procedure I did here. Put a general solution and then come up with the final solution. The final solution is when for the same differential equation is the same. So we don't derive this again and again. Okay, just one time. So as you can see, if X dot at 0 is 0 and X at 0 is 0, then X is always 0 for all time. If one of them is not 0, then this becomes X is not 0. It's going to be a function of time. Now, one thing that you can notice before we stop, just 1 minute, sine omega in t, these are the argument of sine and argument of cosine is the same. And omega nt and omega nt also for cosine. Omega nt is radian per second, and t is what in second. So the answer, the product of omega nt will give us radian, and omega nt in cosine is the same. It's going to give us in radian. So if you want to evaluate X, it means you have to, using your calculator, you have to set the calculator to radian. Usually the default maybe in the calculators is to have degrees. So if you enter this in degrees, you will get a problem. But if you are using Excel, I think Excel is always the default is in radian or MATLAB. Sine in MATLAB is accepting radian. But when you do this in the calculator, make sure that the mode is radian. Okay. Now this is okay. Next time I will talk about more things. Amplitude. And the amplitude of vibration. Okay, so next time I will talk about the amplitude. Any question? Okay, so we'll see you next week.